We have to wait for a moment, let others join. So within a minute, we shall continue with the oxidation states. So we shall continue with the oxidation states. Just now we have seen that lanthanides belong to third B group of the periodic table, and hence the group valency is attributed to all the lanthanides, that is the +3. So +3 is regarded as a principal, major or common oxidation state shown by all the lanthanides. And we also defined that the oxidation state can be defined as it is a numerical value with sign of charge which an atom appears to possess in an element, that is known as the oxidation state or oxidation number. In this regard, just now we have seen that all the lanthanides, they do display +3 as a major or common oxidation states. Now we shall switch over to the remaining oxidation state, that is a divalent and the quadrivalent or the tetravalent. So again take your notebook and you have to work out with the remaining oxidation states. Now first of all, we shall have a look at the lower oxidation state as a +2. It is revealed that not all the members, they do display +2 as a minimum or lower oxidation state. There are only few members, they do display a +2 as a major or common oxidation state. So here the atom number 60 atom number 60 is a neodymium. We have to write Nd+2. So you have to write neodymium +2 as a lower oxidation state. Then 62 samarium shows a lower oxidation state as a +2, samarium +2. Then europium EU +2. Then atom number 69 thulium shows +2 oxidation state. So Tm +2, thulium +2, and ytterbium +2. So these are the 5 members. They do display a divalent oxidation state, that is oxidation state of +2, that is a neodymium atom number 60, samarium atom number 62, europium atom number 63, and thulium atom number 69, and last is the ytterbium atom number 70. So these are the 5 members, they do display the +2 as a lower oxidation state. That is all these members, they are having the divalent oxidation state. So if we look at samarium +2, samarium also shows +3 oxidation state. Neodymium +2 and +3. Then europium +2 +3. Come to thulium +2 +3 and ytterbium +2 and +3. So these are the 5 members. They are having multiple oxidation state, that is a divalent and a trivalent. Now come to atom number, the oxidation state, that is +4. Now cerium +4. So in front of cerium you have to write +4. So cerium do display two oxidations, different oxidation states as +3 and +4. Then next member is a praseodymium, which shows +4 oxidation states. So Pr +4. Then Nd atom number 60 that shows plus 4 oxidation state. So cerium, praseodymium, neodymium 58, 59 and 60. These are the members. They do display plus 4 oxidation state, and there are again two members. Those can also show the oxidation states. That is atomic number 65 is a terbium, which shows the higher oxidation state as plus 4. So you have to write terbium plus 4. Then 66 is a dysprosium plus 4. So we can see that terbium shows two different oxidation state as a plus 3 and plus 4. Dysprosium plus 3 and plus 4. And cerium plus 3 plus 4. Praseodymium plus 3 plus 4. Neodymium plus 3 and plus 4. So not all the elements they do display either plus 2 or plus 4 oxidation states. There are few members they only display these different oxidation states. So the minimum oxidation state shown by all the lanthanides is a plus 2, and maximum oxidation state shown by the members is a plus 4. Only 5 members are there which do display highest oxidation state as a plus 4. Now at the top we have written as oxidation states and outer electronic confusion of. Now we have to arrive at the outermost electronic confusion of all these different oxidation states. So how can we write the outermost electronic confusion of all these elements that we have to see? Now here we know that in the beginning we have seen that 6s orbital being filled at barium. So after 6s being filled at barium, the incoming electrons have now been added to 5d orbital as we know. So those electrons which are present in the 6s orbital, or those electrons are occupied firstly, those are to be removed first. For example, consider the electronic confusion of neodymium having the electronic confusion 4f4, 5d0 and 6s2. So to show plus 2 oxidation state of neodymium, we have to remove these two electrons from neodymium. So after removal, what is remaining? 5d0 and 4f4. So into bracket we have to write 4f4. So you should write neodymium plus 2. So during exam time, sometimes you will be given the oxidation state and you have to ask to write the outermost electronic confusion. So after loss of 2 electrons from 6s, remaining electrons are from 4f orbital. So 4f4. Come to samarium. Now samarium having the electron confusion as 4f6, 5d0 and 6s2. So to show plus 2 oxidation state, samarium should lose these 2 electrons because those are filled very early at barium. So remaining is 4f6. So we have to write 4f6. So write down like this, for samarium plus 2 is a 4f6. I think if you written, we shall move further at europium, atom number 63. If europium has to show plus 2 oxidation state, then it should lose these 2 electrons which are filled first. So what is remaining? 4f7. So these are the members. They are having outermost electronic confusion as 4f4, 4f6, 4f7 after the loss of 2 electrons from 6s. Come to next member, that is thulium, atom number 69. So thulium is having electronic confusion as 4f13, 5d0 and 6s2. So after loss of these 2 electrons, the remaining part is 4f13. So write down into bracket as 4f13. So thulium plus 2 outermost electron configuration is 4f13, then next member is ytterbium. On similar grounds, how can we write? After the loss of these two electrons, the remaining electrons are 4f14 for ytterbium. So ytterbium shows plus 2 shows 4f14 configuration. So f4, f6, f7, f13 and f14. Now come to the highest oxidation state as a cerium. Now, in terms of outermost electron configuration, if we look at the electron configuration of cerium, it is having 4f2, 5d0 and 6s2. So, if cerium has to show plus 4 oxidation state, then it has to lose these 4 electrons to show plus 4 oxidation state. So, what is the remaining after loss of electrons? It is a 4f0. Loss of all the 4 electrons. So cerium can contribute or cerium can share all the 4 electrons during the bond formation, and hence cerium shows a 4f0 configuration. Now come to praseodymium having the electron configuration as 4f3, 5d0, 6s2. So if praseodymium has to show plus 4 oxidation state, then it should lose 2 electrons from 6s and 2 electrons from 4f. So if it loses 2 electrons from 6s and 2 from 4f, the remaining electrons will be 4f1. Only 1 electron is left with praseodymium. Now if you have written, come to next element is neodymium. Neodymium plus 4, see this electronic configuration of neodymium, 4f4, 5d0, 6s2. So if neodymium has to show plus 4 oxidation state, then it has to lose these 2 electrons from 6s and 2 electrons from 4f. Remaining electrons will be 4f2. So you have to write this as a 4f2. Now come to terbium, atomic number 65. Terbium is having the electronic configuration as 4f9, 5d0, 6s2. Then if terbium has to show plus 4 oxidation state, what will happen? It should lose these 2 electrons from 6s and 2 more electrons from 4f. So if it loses 2 electrons from 4f9, the remaining electrons will be 4f7. So 9 minus 2 is a 7. So terbium plus 4 is a 4f7. Now come to dysprosium. Now dysprosium is having electron configuration as a 4f10, 5d0, 6s2. So to show plus 2 oxidation state by dysprosium, it should lose 2 electrons from 6s and 2 more electrons from 4f. So after the loss of 2 electrons from 4f10, remaining electrons will be 8. So we can write this as 4f8. So these are the 5 members: cerium, praseodymium, neodymium, terbium and dysprosium. They show F0, F1, F2, F7 and F8 configurations respectively. Now, after the completion of the lower oxidation state of lanthanides and the higher oxidation states of lanthanides, we can move further with the common principal or major oxidation state of lanthanide as the +3. So, +3, how can we write? Just you try for lanthanum +3. How can we write the electronic configuration for lanthanum +3? If we have to write the +3 configuration of lanthanum, so it should lose 2 electrons from 6s and 1 electron from 5d. Loss of 3 electrons, that leaves no electrons in 4f. So 4f0. Now as written, this lanthanum +3 4f0. Now come to cerium. Cerium, if cerium has to show +3 as a common oxidation state, it should lose 2 electrons from from 6s, and 1 electron from 4f. So if after losing or after loss of single electron from 4f2, the remaining part will be 4f1. So for cerium it becomes 4f1. Now come to praseodymium, the third member. To show +3 oxidation state, first of all, loss of these 2 electrons and loss of 1 electron from 4f, that leaves 2 electrons. So we have to write 4f2. So it is for 4f2. Then come to neodymium. Now neodymium atom number 60. Loss of 2 electrons from 6s and loss of one of the electron from 4f, that will leave 3 electrons with 4f. So we can write this as 4f3. After neodymium, come to promethium for +3, loss of these 2 electrons and loss of one of the electron from 4f5, that leaves 4 electrons. So 4f4. So promethium +3 is 4f4. Then come to samarium. Samarium +3, loss of these 2 electrons and loss of one of the electron from 4f6, that leaves behind 5 electrons, that is 5 4f electrons. So samarium +3 is a 4f5. Then europium. Come to europium. Europium can show, this is a electron configuration of europium. 2 electrons from 6s and 1 electron from 4f is lost. The remaining electrons will be 6. So we can write this as 4f6. So for europium it becomes 4f6. Now come to the next member is a gadolinium. If gadolinium has to show +3 oxidation state, it should lose these 2 electrons. So for gadolinium, 7 electrons are left with 4f orbital. So 4f7. Then come to terbium. We have already written terbium +3. To show terbium +3 oxidation state, it should lose 2 electrons from 6s and 1 electron from 4f9. It becomes 4f8. Only 8 electrons are left with terbium, 4f8. Then come to dysprosium. This is electronic configuration of different dysprosium, 6s2 and 4f10. After loss of 3 electrons, 2 electrons from 6s, 1 electron from 4f, that leaves behind 9 4f electrons. So we have to show 4f9. Then come to next member, atom number 69 is a holmium +3. So for holmium, how can we write? Loss of 2 electrons from 6s and loss of one of the electron from 4f11, which leaves behind 10 4f electrons. So it becomes 4f10. Then come to erbium, atom number 68. To show +3 oxidation state by erbium, it should lose 2 electrons from 6s and 1 electron from 4f12, which leaves behind 11 4f electrons. So 4f11 is the outermost electronic configuration of erbium. Now come to thulium. To show +3 oxidation state by thulium, it should lose 2 electrons from 6s and 1 electron from 4f13, which leaves behind 12 electrons. So 4f12. Then last but one member is ytterbium. To show +3 oxidation state by ytterbium, it should lose 2 electrons from 6s and one of the electron from 4f14, which leaves behind 13 4f electrons. So for F13, you have to write for F13. And the last member, that is very easy, that if lutetium has to show +3 oxidation state, then it has to lose 2 electrons from 6s, 1 electron from 5d, which leaves behind 14 4f electrons. So become the configuration becomes 4f14. So for +3 oxidation state, if you look very carefully, then it is revealed that from lanthanum to lutetium, that is from atomic number 57 to 71, there is a regular loss of electrons to show a principal or common oxidation state, that is a +3. So look at this outermost electron configuration: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 and 14. So we can conclude that there is no any trick that is used to write the electronic configuration for +3 electronic configuration. We can write blindly from lanthanum to lutetium. Just we have to write the electronic configuration from F0 to F14 at lutetium. And here the case is not true for the divalent metallic ions and the tetravalent metallic ions, because not all the members they show the common oxidation state. Some of these members show a divalent oxidation state and a tetravalent oxidation state. So this is all about the oxidation state and the outermost electronic configuration. Now we have to talk about the stability of these different oxidation state. We have to give upon which factor the stability of all these oxidation states depend. Not all the oxidation states are stable. We have to assign one rule which states that the empty or half filled or completely filled electronic subshell, those offer extra stability to the corresponding atom or ion, and hence these are the configurations, they become extra stable. Now, in order to show the extra stable oxidation state, we have to show which are those oxidation states which either fall into F0, F7 or F14 configuration, that is entirely empty, half filled or completely filled. See the divalent oxidation state. This is F4, F6 and F7. That means amongst this here, europium, you have to mark with asterisk, europium +2 is extra stable. Similarly, if you go down at ytterbium, so ytterbium also shows 14 F14, that is completely filled electronic subshell, that is ytterbium +2 is extra stable. So amongst these divalent oxidation states, these oxidation states are simply stable, but the extra stable oxidation states are only two, that is europium +2 and ytterbium +2. They offer extra stability because of completely half filled and completely filled electronic subshells. Now come to the higher oxidation states of lanthanides. We have to assign this rule F0, F7 or F14 configuration. So with regard to this, cerium +4 having F0 configuration, so it is extra stable. Now if we move downwards, then terbium +4, that is having 7 electrons. So mark terbium +4 as again asterisk sign, because it shows F7, that is completely half filled electronic subshell. Now no any other element is there which is having extra stability. So only two members amongst highest oxidation state, that is cerium +4 and terbium +4, they show empty and completely half filled electronic subshell. So here praseodymium +4 and neodymium +4 are only stable, and dysprosium +4 are only stable, but the extra stable oxidation states are cerium +4 and terbium +4. Now We can apply the same rule to the plus 3 oxidation states also. Come to this lanthanum, first member for 0 configuration, extra stable. So mark lanthanum plus 3 as extra stable with the asterisk sign. Now if we move downwards, then here F7 gadolinium plus 3, mark this gadolinium plus 3 as extra stable. So if we move further, come to lutetium atom number 71. This is again extra stable because of F14 configurations. So lanthanum, gadolinium and lutetium, these are the three members, or these are the three trivalent oxidation states which are extra stable. Rest all the oxidation states of the members are only stable, but the extra stability of these elements associated with empty, half-filled and completely filled electron subshells. So here you have to write in your notebook, make a asterisk sign, and here you have to write like this: extra stable oxidation states. You have to write this because during our study one should identify why we have made a asterisk sign for only few members. That indicates that these members or these oxidation states are extra stable oxidation states. Now here, just now we have seen that these elements, they do display a lower oxidation state of +2, then higher oxidation state of +4. So these members, they are having +2 and plus neodymium +2 and samarium +2. The existence and the stability of these oxidation states, including this thulium +2, these are only stable, but their stability cannot be explained on the basis that they acquire either F0, F7 or F14 configurations. So here it is seen that, look at this thulium +2. Thulium +2 is having configuration as 4f13. It is short of only one electron so as to complete its completely filled electronic subshell, even though it is stable. So this stability cannot be explained on these basis. Again here, come to samarium. This is having a short of only one electron so as to complete its 4f7 configuration, which is extra stable as compared to europium, even though it is stable, but it is not extra stable. Similarly, we can also explain this stability also here. So here, this is having one more extra electron, but it is stable because it is having F8 configuration. So the stability of these different oxidation states cannot be explained on the basis of acquiring their either divalent or tetravalent oxidation states. So we can, in general, we can conclude that lanthanides, they do not show higher oxidation states. Those are noted or those are recorded in this particular tabular form, that is +4. They do not display any oxidation state other than +4, which is shown here. That means they can only contribute maximum of 4 electrons for bonding. This indicates. So the plus oxidation state of neodymium, just now we have seen that with 4f configuration. However, it cannot be explained by any of the other reasons, that is F0, F7 or F14 configuration. The stability and the occurrence of all such oxidation states may be explained by some other or more important factor. There may be some kinetic factors may be associated for their stability. These factors are based on the highly complicated thermodynamic and kinetic considerations. So this is how today we have completed two important points with regard to the electronic configuration and the different